thanks everyone to be here, and thank you, Maureen, for the excellent presentation. Now the pressure's on me. So now, today I'm going to talk about how to enhance the submergence tolerance in rice. Before my presentation, I just want to talk a little bit about me. So you can see from college station to the place I was born is not on the same page. It's about 8,000 miles away from here. So this is like the ocean and the mountain are the environment where when I grew up. So this is Taiwan, and I live here. Taipei is there, all in the middle of the mountain. So we have more than 200 mountains higher than 10,000 feet. And so in this area we grow like fruit. All this area grow rice, and some fruits like peach, apple in the mountain area. So my family grows coconut tree and rice. So I come here to do rice research. And additional for peanuts. So one part of my research are for peanut disease resistance and yield quality, and another like 70% is for drought tolerance and submergence tolerance. So today I'm going to talk about the submergence tolerance. So for those who have seen rice, you will think why we need the submergence tolerance for rice, because it's growing the paddy with flooding like everywhere. But you can see this is my field after Hurricane Harvey, 2017. I was doing drought treatment. And it became like flooded. I cannot even see my plants. So due to the climate change, the global warming, which is true, so this kind of like rapid flooding or like in some place there's never flooding, but due to the climate change, it becomes more and more. Like take 4 months for example. So we need the drought submergence tolerance gene for rice. So in rice, we have two kind of mechanisms for submergence tolerance. You can think like easily. The first way is they keep growing faster than water, so they can breathe. The other one is they stop, like hibernate. So they will stop there. When the water gone, they will like active again. So this is the submergence 1 gene. So submergence 1 gene is a very strong submergence tolerance gene, which been cloned in 2006 and released the cultivar in 2009. So from here you can see these are the experiment plots in Erie. For the label with plus means have submergence sub 1 gene. For the minus is without submergence, like sub 1 gene. So you can see it's huge difference, like with or without this gene. So today I have 3 important material. One is IR64 sub 1. IR64 sub 1 is like introgress sub 1 gene into IR64. Then I have another material, Ciherang sub 1. Ciherang is an Indonesia like very famous rice. So they introgress sub 1 gene from IR64 sub 1. Then to breed Ciherang sub 1 in BC1F2. So we have Ciherang sub 1, IR64 sub 1. In 2017, another research shows that between Ciherang sub 1 and another sub 1 variety, we do the QTL mapping and found a novel gene, because both of them have sub 1. So when do a QTL mapping, you can ignore the sub 1 effect. Under this kind of situation, we found another gene called Q sub A. So it's become my experiment purpose. The first one is to characterize Q sub A, to understand like more about this gene, how big is the gene, and what is the mechanism behind that. Another one is to develop the neos for cube sub A, which means the background are same, but the difference between them is with cube sub A or without cube sub A. So this is the outline for me today. First, I use whole genome sequencing and assemble a genome. Try to find where is cube sub A in this background. Then, based on the sequence data, I can design a marker to develop the neos. Then, if try the traditional way, like a marker base, how about if it's not work? So we have plan B, which is use gene editing to knock out sub 1. So if we knock out a sub 1, we can only focus on sub 8 itself, because sub 1 is very strong gene. If the cultivar has both sub 1 and sub 8, you won't able to distinguish with or without sub 8. So we need to remove sub 1. And then we do the RNA-seq to study the RNA expression for with sub 8 or without sub 8. So we have two parents, Shiheran and IR64 sub 1, and their kind of progeny, Shiheran sub 1. We send 3 variety to do whole genome sequencing. The idea about whole genome sequencing is like you send 3 genomes, like they are very long, and you like make them become small pieces. My sequence is 150 base pair. The reason why we don't just sequence the whole genome, because we don't have enough money. We definitely can do PacBio to assemble the whole genome, but we only can do 150. But under this situation, 150 is good enough for our research. So after sequencing, I will get a lot of like millions small short sequence, like 150. Then I assemble them, become scaffold, and become a genome. So after this, I will get 3 individual genomes for IR64 sub 1, Shiheran, and Shiheran sub 1. So this is how the genomes look like. So the blue means these pieces are from Shiheran. The red means it's from IR64 sub 1. And the green means from somewhere else. Means it's not similar like Shiheran and not IR64 sub 1. So on chromosome 9, you can see the big red piece. This is the place for sub 1. So you can see clearly sub 1 is from IR64 sub 1. And for sub A, this is the region for Q sub A. You can see in this region, most of part are from Shiheran, with some small, very small snips or small region from IR64 sub 1 or from somewhere else. So with this information, we can develop the marker to screen the population. So the idea about sub A neo, we cross Shiheran sub 1 and Shiheran, self the F1. In F2, we're able to get different combination between sub 1 and sub A. Our purpose is to obtain group 3, which is without sub 1, but with sub 8. So in 2017, we import the seed from Philippines. Because it's import from Philippines, we need to under quarantine for 1 year, like 1 season. To increase the speed, we do the pollination in a quarantine greenhouse. So rice is very small. The way we do pollination is we need to emasculate. Like we cut the small hole, like 1/3, then use vacuum machine to remove the answer. So it will become like the group number 3. Then we collect the pollen, then do the pollination. And this is how the F1 looks like. Without the hole, so the shape will look a little bit weird, but it's the first step to see if we have F1. After this, we need to germinate the seed, run with codominant marker to make sure it's F1. So after we measure it's F1, then cells to F2. In F2, we use 614 F2, then screen by the marker for sub1, it's ART5 and RM8300. So after screening 600 progeny, we got around 71 is without sub1, but we don't know sub8 yet. We try to design a marker, but it failed. We try to design like indel marker, then the result shows the deletion is not a real deletion. So we move to SNP marker. So now it's going to be used CASP marker. At first, we thought it might be delay our project, but don't forget we have plan B. So plan B, we use CRISPR-Cas9 to knock out sub1 gene. With this, we can find this is sub1A, the second exon. The black sign means 2 of my guide RNA, so I can tap in the first black and the second black. If everything goes well, it should make a cut in the first and the second. And between these two fragments is very short piece, so we have a good chance to delete the whole region. So these are the idea about how to put guide RNA into a plant. So we have 2 guide RNA put in the vector first, then use this vector to combine guide RNA and Cas9 protein. Cas9 protein is the thing to make the cut, like a scissors. So after everything, we transfer to E. coli and agrobacterium. E. coli, the purpose for E. coli is to multiply, like produce a lot of plasmid, and the agrobacterium is to infect the plant. So after put inside that, we only do 1 Sanger sequencing because it takes about more than a week to get the result, and we don't want to be delayed. So we use the basic enzyme cutting to make sure if everything is correct. So based on the sequence, we have the final destination vector sequence. From that, we can design what enzyme can make what cut, and the cut with what size. So based on like regular gel, we can check if it's correct. So this is just like a simple transformation into agrobacterium. So after you have the construct, you have the bacteria. The next point is how to deliver into plant. Because the rice I work on is indica rice, which is no standard protocol for transformation. So I try all the combinations we have, like material seed to agrobacterium to gene gun, or immaterial seed to agrobacterium gene gun. Each of them takes about 6 months to get a plant. So there's the purpose for this is similar. The only difference is with agrobacterium, in the future it will be considered more like GMO. But with bombardment, if you can get rid of your Cas9 protein, it won't be considered a GMO. But for my research, it doesn't matter. The most important thing is I want a plant. So these are the current status I have. Like they are from the bombardment. Then, so the process for transformation is I have either mature seeds or immature seeds. I need to have callus. Then treat callus with either gene gun or the agrobacteria. So these batch are from gene gun. And after gene gun or agrobacterium transformation, we have 3 selections. to make sure these callus with the selective marker, which is hygromycin. After selective, then regeneration. So from a small callus, they regenerate to shoot, then and they will grow like small roots. After they have like enough of roots, we can transfer into the soil. So now they have their roots, and I'm still waiting. I did not have chance to check them, like the Sanger sequence yet. So other than this, we also use transcriptomic study for helping us know more about Q sub A. This project, like this part of the study, was collaborated with UC Riverside, Dr. Julia's group. So based on 3 genomes, we can predict the gene from a sequence, but it's just a predict. Nobody knows it's true or false. Nobody knows is this gene going to express or not. So we do submergent treatment, then extract the RNA and do RNA sequencing. So after all analysis, we do the goal enrichment to see what kind of function is triggered under submergent stress. So this, because we don't have the NEO yet, so we use M202 sub 1. M202 sub 1 is with sub 1 gene, but without sub 8. So we use Chiron sub 1 compared with M202 sub 1 to compare sub 8 effect. Then we found maybe it could be related to like programming cell death or the amino acid metabolic pathway. So here it goes to my conclusion, like Q sub A region is mainly from Chiron, but with small fragments from other source. We don't know if it's functional yet. And based on the candidate gene from RNA-seq analysis, we will think this function might be related to programming cell death and amino acid, and could be about like ABA or insulin signal pathway. So our future work is we will do the physiological and molecular analysis for testing our knockout line from CRISPR. We will do Sanger sequencing to make sure if deletion is there, and we will do the phenotype checking if submergent tolerance is there. And I think that's all. And I would like to thank my committee members, Dr. Septi, Dr. Daphne, Dr. Thompson, Dr. Tabli, and Dr. Wang. And my colleague, Becky Kim, he was the postdoc in our lab, and now he moved back to South Korea. All my transformation and pollination technique was taught by him. Then I want to thank Ranjita. She is my lab mate. She gave me a lot of support for study, especially for English. I will ask her to check my email before I send it out. Then I thank Sudeep. He has very good experience in transformation. So when I do immature embryo transformation, he gave me a lot of help. And our lab technician, Oneda, and Dr. Nithya for helping me design the Cas marker, and all our lab members from Dr. Septi and Dr. Thompson's lab. For UC Riverside, Dr. Julia and 2 of her postdocs. Then for Dr. Tabian and Kirsty Patrick, they are from Beaumont. The quarantine greenhouse was under-monitored by them, and some of our field study cannot finish without their help. Then Dr. Fujin Wei, Yiping Lai. These 2 are my friends, and they are computer science major. Because I'm not good at coding, I don't have background with that, but when I do this project, I need a lot of coding work. So for all the error, all the problem I cannot solve, they help me a lot with patience and show me everything. Then Liang, he was the master student from Dr. Staley's lab, and he also is the expert for caps marker. So when something's not working, he gave me different suggestions and gave me many ideas. And Marco Myra's lab, their lab is in Burlau Center for Transformation. So I spent more than a year in transformation, and they can help me to solve all the tricky problems. For example, one time my cat is like dying. I cannot find any reason. In the end, they found the growth chamber is too hot, and the temperature inside is different from the monitor, which nobody can find this problem without a lot of experience. With that, I can take any questions. Thank you.
How long does the sub-1 and sub-8 genes allow rice to be submerged before dying?
The record in Erie was 25 days.
Is it with both the genes or just sub-1? Is the record with both the sub-1 and 8, or is it with just sub-1?
With both genes.
With both.
Actually, that's in the field you can see there's ISCC for sub-1, Tiarang sub-1, and other. So some with sub-1 and some with combined. But then we can see that Tiarang sub-1 is more superior than the rest of the sub-1 variety. Like the yield is much higher. Actually, we published that work actually. So, Tiarang sub-1 actually has yield as higher as Swarna sub-1, and Swarna sub-1 itself actually is Tiarang sub-1 has shorter duration of maturity, but then the yield is the same as Swarna sub-1 which is longer duration. So it shows that Tiarang sub-1 actually more superior during sub-1. Because compared to ISCC for sub-1, Tiarang sub-1 is much higher here under sub-1. So we predicted that because of the additional features.
In your RNA work, I don't know if I missed this, but where did you take your tissue samples from?
From the meristem.
So you did from what? I was just wondering if you looked at the difference between leaf and root tissue to see if there's more of like an expression in the tissue level. Like if it, I'm not sure what the subgene, if it's a root-based resistance maybe or something like that.
Actually, the gene, there's already research in gene before. The gene actually express more in the stem, especially close to the soil.
Okay.
So that's why we can go at that part.
And if there's no more questions, thank you so much.